All right, so just a quick recap. We have been doing these workshops, I think, for 3 weeks now. So just wanted to go over what we covered so far. As George said, we talked so far about Flyte plugins. There were 3 of those 3 workshops. You can hopefully go back in history and watch these. I think they're also posted in our docs. The first was the task template based plugins, and we give an example of Snowflake. These are plugins you can write completely in Flyte. You can customize what container gets run when we encounter one of these tasks in a workflow. And you are given the task template, which is the Flyte representation of the task, or the serialized representation of the task. And your implementation of the plugin is responsible for how to execute it. In the example of Snowflake, takes the task template and just extracts the SQL query from that, and some connection information, and use that to talk to Snowflake backend and authenticate and run the SQL query and write the output. And then the second one was the maybe core task plugins in Flyte, if for the lack of better terms, better name. And we give an example, I think, of a Spark task, if I recall correctly. Those tasks, you get complete control over how they get serialized. And you have sort of 2 options. You can serialize, you can try to map user code into one of the existing task types. So maybe you want to introduce a new syntax for writing a Spark task, or and so on, and you can handle the user code and then serialize into an existing Spark task structure, or it can be completely different, completely new. If it's a completely new task, template format or data, you will likely want to implement an equivalent backend plugin. Those are the ones we will talk about today. And then lastly, we talked about type transformers. I think there was an example of pandas data frame, if I'm not mistaken. These allow you to, again, completely living in Flyte to transform a sort of a Python type, or a type that exists in Python, or in the Java case, type that exists in Java, into a Flyte understood type. And those types, once transformed, can then be passed around to other task types, other languages. They're fully interop in the system. They can be checked in the compiler and all of that. And you're also responsible for the conversion the other way around. So once a task is called with the transformed type in Flyte literal, you're also responsible for transforming it back into the Python equivalent type, right? And today we will talk about K8s plugins, Flyte K8s plugins. So we'll start off with what are those. It's a way for a plugin author to extend Flyte to seamlessly integrate into existing Kubernetes objects, and offer sort of a full interop system between these Kubernetes objects and the rest of the Flyte tasks you have in your workflow. And once they are in, once you get all of this done, you get all of the goodness of the rest of the Flyte tasks. Things like passing inputs, outputs to these objects, right? So Flyte will take care of sandboxing the inputs and parsing out the outputs and all of that. You get to be able to orchestrate between different object types in Kubernetes and completely non-Kubernetes objects as well. So maybe you run a query and then you run a Kubernetes object, and then the third one is, a task template based object, right? So you get full interop this way, even if these systems don't really understand each other. You make them talk Flyte, right? You get lifecycle management and retries and a bunch of other things. I wanted to talk about why would you go with implementing one of these backend plugins, as opposed to maybe you can put all of your logic into a Flyte Kit plugin, right? Because you can when the time when your task plugin is called to execute, you can decide to then create the Kubernetes object, create a kube client, create the object, monitor the object, and do all of that in your Flyte Kit code. And you certainly can, and maybe even you should, just to validate that the idea you have for writing this plugin is usable and people want it. But once this is ready, there are some advantages for writing a backend plugin that, as of now, are not easily done when you just write a Flyte Kit plugin. These are some of them. So one, you get lower runtime overhead. And what I mean by that is once your task, once the user code is serialized into a task template, there's no more containers you need to run to start this Kubernetes plugin, right? The code will go to the task template code will go to the backend. The backend will decide to invoke your backend plugin, and then you are free to do whatever, right? Whether that's creating Kubernetes objects or some other backend plugin type that maybe just calls a backend service to run a SQL query. There could be no containers involved. There's no Docker image download time and container start time. Like all of that is completely eliminated when needed, obviously. Scale, and this is sort of related, and because of that, because you don't have to start a container for every task instance of this plugin type, you can scale to millions with like very little overhead on the system. Another benefit is, again, as of today, you get to customize the links that show up in the UI. So when you click on a node in the UI, you get on the side panel, and you have links for logs and whatnot. If you write any backend plugin, you get to customize those, add new links, and so on. We're always looking for ways to expose some of these features to, again, the Flyte Kit plugin system. So it's because we think it's an easier way for people to build plugins and it's completely insulated. So it's a very good environment to experiment and try. Like it's a low barrier to entry environment for people to start extending the system. But as of now, this is one of the functionalities that are only available in backend plugins. You also get resource or capacity management sort of for free from Propeller, from the backend plugin system. You can decide, some projects, some Flyte projects only get to launch, 10 Spark applications at any given point, right? Or you can like distribute the capacity however way you want. Maybe you have SQL queries and you don't want to overwhelm the external system because everybody's calling the same, endpoint to send queries to, and you want to throttle them, or you want to just impose limits on every project or every workflow. So you get a lot of flexibility and sort of for free with just declaratively managing the capacity. The system can impose these limits for you. You also get, and this is specific to K8s plugins, the system will fully manage the resource, the K8s resource lifecycle. And your plugin, like the code you will have to write, is very limited to the pieces of code that we can generically implement. And we'll talk about that in a second. But before I do, just a quick primer for about K8s objects lifecycle in general. And these objects really offer the basic premise is they give you a generic CRUD API interface. You can create, you can read, update, and delete these objects, right? So, and it's a very generic standard interface. You can interact the same way with any Kubernetes object, whether they are like natively comes natively with Kubernetes, like config maps and pods and whatnot, or you import them into the system through custom resource definitions. They all have the same interface. But in sort of practice, there are two sides of this. There are people who create these objects and are interested to utilize them, like calling them consumers. And then there are operators. The operators are the processes that are responsible for actually executing or making some change based on the contents of these objects. From a consumer standpoint, you usually go through this sort of cycle of creating an object or maybe modifying it for some objects that do support modification after creation. You are monitoring it, so you want to see, did it finish executing? Is it failing? What's happening, and so on. So you go into this monitor check frequently, and when it's time to delete the object, or when you're done with the object, you can finalize it. Again, this is an optional step, allowing the system and the operator to know that you are no longer interested in this object, right? I am done with it. And you can also explicitly call delete, right? You can, if you want, if it failed, maybe if you want to clean up yourself or whatever, you can explicitly delete these objects. From an operator side of things, so the thing that's executing this object, you usually go through this reconcile loop, and it's basically you are monitoring changes to objects and new objects that show up, and you want to do some change. In the case of the pod operator, for example, you will go maybe launch the pod in or assign the pod to a node and launch it in a kubelet, or if it's a deployment, you create a replica set or whatever, right? Or in the case of Flyte workflows, our operator is Propeller, and it goes through the workflow to execute the steps, right? So you do some work, and then you mutate the status of the object to reflect what you did. Did I, successfully create a pod, or I successfully created the replica set, and what's happening? Maybe it's a deployment, and you say the user said, I want 5 instances of this service. The status, the deployment operator might say, well, I deployed 3 of them and 2 are remaining. So you put in the status of the object what's the current state of things. And you go over and over again, right? So it's sort of a state machine, and you manage your own state machine this way until you try to get to the desired state of the object. And in the case, again, of there is a cleanup needed, you also do this finalize step where you maybe delete external resources you created, or maybe put in the final status or do something, right, with the object. And then you finalize it, and now it's, the system is free to delete it. You no longer can do anything about it. Right, what we are trying to do with these Kubernetes, with the Flyte K8s plugins, is simplify the left side here. So simplify being a K8s object consumer, allowing you to create, monitor, finalize, delete in a very safe environment or framework. And as I was saying earlier, integrating into the rest of the Flyte ecosystem. Typically, this is where you start, right? The user, you have to decide first what you want the users to write. I have 2 examples here on the left side of a Spark plugin on the top, right? So this is how you write today, how you declare that the user declares that they want a Spark task. They write just a regular, what looks like a regular Python function, right? With inputs, outputs, and the annotation, the add task annotation. And the only difference you see here is this task config equals Spark. And this is sort of the entry point to using your plugin. So now and we'll look at this code in a bit. Now, the system will know that this is not a regular Python task. This is a task that wants to use the Spark plugin. It will invoke that. It will pass all the information the user declared here. In this case, the Spark config with memory and instances, and then the plugin will take this part and convert it to the right side. This is the output of the task template, right? And your plugin gets to decide what goes in here. I deleted a bunch of things from the task template, but you can see the top 3 fields here. The type, config, and custom are probably the things you will deal with the most. The type is what tells the rest of the system that this task is a Spark task. It's not a Python task. It's not an array job, right? It's a Spark task that was generated by some plugin on the SDK side, and this name decides what backend plugin can pick it up. The config and custom are 2 fields that are given to you. They have differences. The config is just a key value map, and custom is a full JSON object where you can fully pass or customize what to pass to your backend plugin, right? So your SDK plugin can say whatever, it can set all the fields needed so that the backend plugin can do the work you want, or the user wants it to do. I gave 2 examples here of plugins of user code, the user side of things. The top was the Spark. The bottom left here is an Athena task, just to show that we don't care as much about how you expose the task to your users. It can be a regular Python function. In the case of Athena, it's just a query wrapped with some other fields. It can be, maybe you have your own DSL that you expose to users. That, right, doesn't matter. At the end of the day, you get to decide what goes into the task template, and that's what this should have all the information you need for your backend plugin to fully execute this task. Continuing on, so once you have the task templates, right, and then the user, let's say, wrote the full workflow using this, we create a workflow CRD every time you launch a workflow. And then Propeller is the operator in this case and picks up the workflow and starts executing these nodes. In this case, let's say the N1 was the task that we wrote earlier. And this is where Propeller starts invoking, or trying to associate which plugin should handle this task, right? So it will look at the type, you say, well, this is a Spark task, let's say. So it will invoke the plugin registered for this. And we have a sort of a base implementation, we call it Flyte K8s. This is the base implementation that handles Flyte K8s plugins, right? So as I was saying, we try to automate as much as we can from the operations you will need to do as a consumer of a K8s object. And so all the operations that you don't need to customize in your plugin are handled by this base object. The Propeller can call handle, abort, and finalize, and we'll talk a little bit about the sort of the state machine here. When does it call what? And this base takes care of the interaction with API server whenever we need to create an object or delete an object and so on, right? The part that it will need to customize, though, is, or doesn't know how to handle, is given this task template that we looked at earlier, like Spark, for example, how do we convert that into a Kubernetes object, right? It doesn't know which Kubernetes object, doesn't know how to translate field X to field Y in the object and so on. This is where your implementation of a plugin is. You implement these main 3 functions. Build identity resource. This just returns an empty object. So like in the case of Spark, it returns an empty Spark application object. And we'll talk about how we use these in a bit. Then there is a build resource, which takes care of translating the task template into Kubernetes object, so the full object. And then the base, the Flyte K8s base takes care of persisting this object in Kubernetes and retrieving it and monitoring it and so on. And then the last one is get task phase. This is how we ask you, the plugin, the author, to translate from a Kubernetes object state to a Flyte phase. So this is us asking you to translate back, did the operator of this object decide that it succeeded, it finished, is it like blocked waiting for resources, or what's going on with it? And you should know that and look by looking at the Kubernetes object and tell us back, well, this state here means that in Flyte land or Flyte lingo, right? So these are the really only 3 functions you need to implement in your Kubernetes object, and it just plugs into the system, and you get the full lifecycle management and all of that. The way our base implementation knows about what state things are is that we store a state, right? So I was saying we fully manage the lifecycle of your Kubernetes object, and to do that, we need to know, did we launch the task yet? Is it running and waiting for it to finish, or waiting for resources, or it's not scheduled yet, or is it failing? Like, we need to know that, right? And we store this into the CRD. And every time Propeller wants to check status for a node, let's say N1, that's a Spark task, it will pass this part of the state to the plugin to say, well, this is the last state I know about the task, and then we take this and try to understand if things changed. Maybe it's still the same. Maybe we launched the pod and it's still waiting, it's still running. There's no state change. That's okay. We'll come back and say, well, nothing changed, and Propeller will keep pinging the plugin every once in a while. There are rules. There's like time-based and event-based triggers for this, but at the end of the day, it will, at certain points during the time of execution of the workflow, it will call the plugin again to say, well, did it finish yet? Give me the new status, and so on. And this is where the base implementation will call your plugin to get the latest updates, and then update the state in the CRD, and keep doing this over and over again. I wanted to talk about when do we call these functions, and this is the sort of the state machine that the base implementation handles for you. And we store the phase and handle the state machine state into the workflow CRD for persistence. It's durable, and it's guaranteed to only progress forward. There are some guarantees that you get for free by just leveraging the state we expose to your plugin. We start off with, we haven't started yet, right? It's the first time we see the node. The base implementation will then call your plugin to say, well, build me the resource. Well, here's the task template that the SDK serialized. Build it into some Kubernetes objects that you want me to persist. And then the base implementation is the one that will call K8s create. So it's the one that will make the API, Kube API call to persist this object in etcd, and then the corresponding operator will pick it up, and so on. Once it's created, we go into this, and this is usually where we spend most of the time, the sort of intermediate states. Maybe it's waiting for resources, maybe it's running, and things can take time to run, and so on. And we'll keep calling, right? We'll keep staying in this sort of part of the state machine for a while. Every time we come here, the base implementation will call you and say, build an identity resource. An identity resource, as I was saying, it's just an empty shell. It's just the Go type that corresponds to your K8s object. We take care of then filling in the standard stuff that Kubernetes exposed, like the name of the object, the namespace, the annotations and labels and whatnot. And we retrieve the full object from Kubernetes, whether that's from the cache that, again, we take care of automatically refreshing, or if it's not yet in the cache, we go make the Kube API call to retrieve it and cache it. So we bring back the full object, the latest object we know of, that from Kubernetes. And then we call you again. We say, okay, so here's the full object. Give me now the state that the Flyte system can understand. because we cannot, like all of the Kubernetes objects, store their phases in slightly different places. There's no standard way of doing that, and there's no standard way of parsing this out or understanding what phase did they succeed or not, kind of thing. So it's your plugin implementation again that will take care of this. There are a couple of operations that can happen sort of out of band through Flyte. So one of them is abort. Let's say the user in the UI decided to abort the entire workflow. So Flyte will take care of making sure that if there is anything that's currently running in the workflow, that we make sure they are cleaned properly, and we call your plugin to again build this identity source, and we make sure we delete the object from Kubernetes so that we don't leave it, running and consuming resources while the workflow is aborted and the user is no longer interested in the output of the workflow anyway. Finalize, a little bit trickier, but and the K8s delete here is also customizable. There are some situations where we don't delete, or we can decide not to delete. But for the purposes of this discussion, let's say, we again from the plugin implementation side, we just call the build identity source, and then we take care of, or the base implementation takes care of doing the right thing. So with just these three functions, you get the fully sort of integrated into the Flyte backend system. You don't have to worry about the objects leaking or creating duplicate objects or redoing the work over and over again. You get retries sort of for free, like the implementation for making sure you get sandboxed inputs and only like sort of one instance of this task will be running in a given workflow, or like one retry of this task will be running at any given point. So all of these guarantees just happen for you. You don't have to think about them. You don't have to code for them. You just get them for free. This is sort of the overview, I guess, about all of the magic behind running these plugins. I wanted to go over a couple of examples. We'll pull in code now. We look at FlyteKit, the Athena, and Spark. So these are the two examples we looked at for the user code, and how are they different from FlyteKit side. And then we'll spend a little bit more time looking at implementations for K8s Pod and the Spark plugins, which are the backend implementations, and what do you really need to do to implement one and get one like loaded and integrated in the system. So and all the links I will show now are included here, so you have to remember them. Did this work? Did it switch to the code? Get thumbs up, down. Yes, okay, right. So I wasn't sure if it will switch with me. All right, so this is the first one I want to look at, looking at what is exposed in your FlyteKit. This is the base task, sort of abstract class of sorts in FlyteKit that you get when you implement a plugin, a task plugin in FlyteKit. These are the two things I was mentioning. So you get to override these two functions to return whatever additional information you want to include in the task template. So you just either return essentially a JSON object in custom, or a key value dictionary for config, right? And it's up to you what you need to do or what you need to expose or serialize in the tasks template for your backend plugin to execute correctly. I wanted to go over the couple of plugins I talked about just to show where this is. So this is the root of FlyteKit. We have a directory here of all the FlyteKit plugins. All of these get compiled and packaged and shipped as separate PyPy packages. You can download one or none. You have to download the one you want to use, obviously, but it's just to say that you can implement like a FlyteKit plugin completely sort of out of repo So when you are experimenting, maybe you don't have to modify FlyteKit or change how people install FlyteKit. This remains the same, and your plugin is just an additional package they install, and they can start using your the new plugin or new functionality. This is the plugin, the pod plugin, and you can see the only some customizations here for how the container is serialized and whatnot. But the one I wanted to show is it only needed to, it didn't need to fill in the custom part. It just needed one config to be passed. This is primary container name, just a string to string, right? So this is the one thing that we'll get, or one additional thing that the backend plugin will get from this FlyteKit plugin. The Spark one is a little bit more complex. So again, it inherits from, again, eventually the base task, and it returns, it customizes the custom field. It stores a full protobuf object. In this case, you don't have to. Again, you just it gives you a full JSON object. You can store it however you want. We chose to store a protobuf object here. It's a Spark job, proto with a bunch of fields that Spark needs to bring up a Spark cluster. In your case, maybe simpler, even more complex, but you will pretty much just want to start with one of these files and then customize your way until you have all the information your backend plugin needs to execute correctly. On the backend side, these plugins, as of today, again, they are all statically compiled into Flyte Propeller binary, and they need to be loaded using these silent import statements. So every backend plugin you add that you want to load in Propeller, you need to add one more import here. We have we've seen in other places where they sometimes implement a private plugin, right? So it's a backend plugin that only lives in that company. You can replace this main file with your own main file and load your plugins this way. Not the easiest, most friendly way to import plugins, but this is the currently supported way of doing so. And yeah, there are some production systems that are already doing this. And then I wanted to look at a couple of plugins. So this is, I'm looking now at Propeller code base. I will switch to the plugins code base. This is the container plugin. And I want to talk about a couple of things here. The first is this init function. So when this package is imported in Propeller, it's not enough to just import the package, right? The package, when it's imported, needs to declare itself as a plugin. And this is how you do so. You register a K8s plugin or a core plugin or a web API plugin. Those are other plugin types we will talk about in future workshops. In this case, we are registering a K8s plugin, and it has some information about the name of the plugin, what task types that it can handle. This goes back to that string I showed earlier in the presentation, the task template that says, in the task template type Spark. This is the thing that ties these two pieces together, ties the SDK part with the backend plugin. And a few other information here. Then there are the three functions we talked about. The build identity resource just returns an empty pod. Build resource takes the task template from here and converts it into a pod and returns the pod, right? You don't create it in Kubernetes yourself, you just return the pod. And then the get task phase. So this gets a Kubernetes object, in this case, an actual pod. This is sort of the latest version of the pod that the system knows about. And you are asked, your plugin is asked to look into the pod and figure out, did it succeed, did it fail, is it still waiting for resources and things like that. The one thing I wanted to point out, or the additional thing I wanted to point out here, I talked about customizing links in the UI. This is also where you do that. You can look at the the pod, the object, and decide what additional links, log links you want to expose to users. In the case of the pod plugin, it's simple. It invokes the log plugins, and we will also talk about log plugins in a later workshop, to expose all the links for logs for this pod. When switching to the Spark one, it's a little bit more complex, because in the Spark case, you stand up an entire cluster that has a driver pod and multiple executor pods. It has its own UI. There's a history server running centrally that tracks your work, right? So there are a bunch of more logs that we expose in maybe the distributed TensorFlow, distributed PyTorch, operators, or K8s objects. It's also similar. There are like a notion of some driver and executor pods, and you will also want to expose the links for all of them. So that's exactly where you can do that. The Spark task plugin also registers itself same way, and then has again implementation of task phase. This is where it gets a little bit more complex, trying to figure out the right links given a Spark application object. And then just the normal stuff, right? Again, looks at the object state and figure out what does that mean in Flyte lingo and return that. Yeah, this is what I was talking about when I say more complex. So all of this implementation is just to get to compute the right log links for, in this particular case. We can, like, if somebody's interested to go deeper into how Spark does it, we can talk about it, but it's just, I just wanted to mention that this is where the hook you have to do that. The build identity source is still simple, right? Just builds an empty shell object, and then the build resource is also complex. This is all of it, right? So this takes the task template that is passed in, and its responsibility is to build you a full Spark object to return, Spark application. There's a bunch of things. One of them is, in this case, is parse back the custom fields that we looked at earlier into the proto, and it uses that to figure out all the properties it needs to set on the Spark application, what the driver spec and executor spec are, and some substitutions for the command lines, bunch of things, resource requirements that you specified, all of that, and then at the end it just builds you a full the Kubernetes object and return that. And they, right from this point on, these plugins will behave exactly the same, right? From the simple container one to the Spark one, they just need to tell us how to convert task templates to objects, and objects back to the state that we understand. And then the base implementation, the Flyte K8s base, take care of all the life cycle management, because all Kubernetes objects essentially behave the same way when it comes to that. I think that is it. I will be happy to take questions. And I was saying, yeah, these things we looked at are all here. So, pointers to if you want to get started. And we'll be happy to take your questions now.